This machine exists to protect something that may survive for less than a second. Deep inside it, a qubit is isolated from heat, light, vibration, almost everything we associate with the real world. And still, it fails.
So why are the most powerful technology companies on Earth spending billions trying to keep it alive?
A classical bit is dependable, 0 or 1. A qubit can behave like both until the environment touches it. Then the information collapses. One useful calculation may require millions of operations. One small error can poison the result. This is the real quantum race, not the race to build the largest chip, the race to create information that survives.
Microsoft believes the answer may be hidden inside the qubit itself.
Majorana 2 is built around topological quantum computing, an attempt to store information in a form that is naturally harder to disturb. Microsoft reports a 1,000-fold reliability improvement over its previous design, and average qubit lifetimes near 20 seconds. If that protection scales, fewer physical qubits may be needed to build one reliable logical qubit. But this is still a wager. The physics must work repeatedly across a machine large enough to matter.
Google and IBM are making a different bet.
Our logical qubits now operate below the critical quantum
Their
error
superconducting
correction
circuits are
threshold.
fast, manufacturable, and already operating in laboratories in the cloud. Google's Willow experiment showed a critical behavior. Enlarge the error-correcting system, and the errors can fall instead of rise. IBM is attacking the problem as a complete machine. Processors, modular connections, control systems, software, and new error-correcting codes. Their challenge is brutal. Thousands, perhaps millions, of fragile devices must behave like one dependable computer.
But silicon is not the only place to build a qubit. What if every qubit began perfectly identical?
Quantinuum and IonQ trap charge atoms with electromagnetic fields and control them using lasers. Atoms can remain coherent for a long time. They can also connect with one another in flexible ways. The trade-off is speed and engineering complexity. Scaling means controlling an orchestra of light, vacuum, motion, and timing. Atom computing and QuEra remove the electrical charge. They arrange neutral atoms in grids of laser light, reconfigurable constellations that can grow to remarkable sizes.
PsiQuantum wants the information to travel.
Lots of things work. There's just things that are just out of
Its qubits are photons. Light moves naturally through chips and fiber. It does not need to sit inside a massive dilution refrigerator. But photons disappear. Sources misfire. Detectors miss them. A useful photonic machine must overcome loss on an industrial scale. Every architecture escapes one trap and enters another.
Suppose one of them succeeds, what changes?
Not your laptop. Quantum processors are more likely to become specialized scientific engines, connected to classical supercomputers and artificial intelligence. They may model molecules, catalysts, batteries, materials, and medicines in ways that are painfully expensive for ordinary computers. And they may threaten the mathematics protecting today's encrypted communication. One reason the transition to post-quantum security has already begun.
Topology, superconducting circuits, trapped ions, neutral atoms, photons, 5 paths through the same impossible problem.
The winner will not be the machine with the most impressive photograph or the largest raw qubit count. It will be the first machine that turns fragile quantum behavior into reliable, useful work. For now, the qubit is still fighting to survive, and the race has only begun.
What if the winning qubit has not been invented yet? And what if the machine that designs it is already learning?